All right, so let's talk a little bit about similarities with 2D and 3D vectors. What's great about 3D vectors is they're a lot like 2D vectors. We spend all kinds of time on all of these items, and really they carry over nicely to 3 dimensions. So jot these things down as being the same. There are some things that change. We don't really talk about bearings of 3D vectors, but we can still find angles between vectors, and we can still find magnitudes and all this other stuff here. So let's jump into an example. In this first example, I want to find the unit vector in the direction of this vector right here. So remember, let's not confuse the difference between unit vector versus unit vector form. Unit vector form is just the type of notation we use for a vector. In this case, the unit vector form is with your i's and j's and k's. So this is unit vector form, but this in itself is not a unit vector. Remember, a unit vector means the magnitude is equal to 1. And hopefully you can see right away, this magnitude is not equal to 1 since there's one unit in the x direction, 2 units in the y direction, and 1 unit in the z direction. So another way of thinking about this is maybe it's a good place to start drawing this in component form. So let's write I plus 2j plus k as a component, or as a set of components. So this would be 1 and 2 and 1, since this is 1i and 2j and 1k. And if I want to find the unit vector in this direction, really what I'm doing here is I'm taking each one of these components, 1 and 2 and 1, and I'm really dividing it by the magnitude of this vector. I mean, think again about how we did this in 2 dimensions. If I had some sort of a triangle, or if I had a vector that was something like this, and it was, I don't know, let's say 3, 4, obviously this isn't the scale, 3, 4, 5, and I wanted to find the unit vector, I basically scaled this entire triangle. I shrunk it down until I had a unit vector of 1, and to find what this vertical and horizontal components were, basically just divided this by 5 and divided this by 5, since I'm scaling everything down by 5. So let's do that with this. I want to take it back to my 3-dimensional vector. It's the same type of process. Let's find the magnitude of this. The magnitude of my vector 1, 2, 1 is going to be equal to the square root of 1 squared plus 2 squared plus 1 squared, which is equal to 1 plus 4 plus 1, so that's 2 plus 4, so this is the square root of 6. So now all I need to do is to find this unit vector. The unit vector is 1 over root 6, 2 over root 6, and 1 over root 6. This is getting a little squish here. So you know what I want to do? Let's write this in unit vector form. So this would be 1 over root 6 I plus 1 over, or excuse me, 2, whoops, 1 over root 6 I plus 2 over root 6 j plus 1 over root 6 k. And k gets its own arrows too, as well. So there's my unit vector form. This is a unit vector because the magnitude of this is equal to 1. How could you check? Find the magnitude the same way we did before. So here's a U-try that I'd like you to do. This is not finding a unit vector, but this is finding the dot product. This is the same process as with 2 dimensions, and I encourage you to take a look at your resources if you're not sure how to find this dot product, although hopefully by now you do. So give this problem a shot and resume when you're ready to see the answer. All right, so here's my dot product. I took the product of my x components, my y components, and my z components, added them all up, and I get a number. Remember, this is not a vector, it's just a value. And because this is negative, that tells me something about the angle between these two. If I have a negative dot product, then it means that my vectors are moving in opposite directions. Remember that 0 is perpendicular. The dot product equals 0. It's negative when they're in opposite directions. well, I shouldn't say opposite, but opposing. They aren't 180 degrees from each other, but they're in general different directions. And if they're in similar directions, then the dot product is going to be positive. Just a little reminder there. That's all true with three-dimensional vectors. All right, so now let's kind of add something new. This is where things get a little bit weirder. When we talk about collinear vectors, 3D vectors. We can talk about collinear 2D vectors, but it's just a little bit more complex now that we have that third dimension. So we have 3 or more points on this line, and they are collinear if they lie on the same straight line. So that's nothing new. So notice that if I had this line here, A, B, and C are collinear if the vector AB is equal to some scalar times BC. Let's put that in another color. So this is vector BC. Let's change that. So if they are collinear, then really it would make sense that one is the scalar multiple of another. That means that they're in the same direction. But how do you know that they are actually collinear? Well, they would have to, well, they share B in common. So AB and BC, if they're in the same direction, there's no way that I could have some vector AB be parallel to some vector BC if I've got two different B's. So the only way that you have the shared point B is if they're on the same line. So let's talk about an example that uses that concept. I want to prove that I've got these 3 points, and I'll prove that they're collinear, and hence, meaning use that information to find the ratio in which B divides CA. So really what we need to figure out is let's kind of draw what this might look like as an example. So if I were to draw these 3 points just kind of randomly on a line, I could draw it like, let's see, B is dividing CA, so I can draw it just like before, where I have some line that looks like this, and B is in the middle of CA, so let's say that this is C, this is B, and this is A. I really don't know if that works with these numbers. Frankly, I don't really care because I just know that B is in the middle of CA. So now, if I want to find what vector AB is and vector BC is, I'm going to have to do a little bit of math. Surprise, surprise. Let's find what vector BA, or rather AB, is. And that's going to be equal to the difference between all these coordinates. So that's 4 minus -1, and 0 minus 2, and -1 minus 3. And, oops. Let's get rid of that. So the vector AB is going to equal 5, -2, -4. And then let's take a look at what vector BC is. Vector BC is going to be all the C's minus all the B's, so 14 minus 4, -4 minus 0, and -9 minus -1. That's going to come out to be 10, -4, and then -8. All right, so if if these things are collinear, then notice we already have B as a joint common point between them, so we just need to prove that this one is a scalar multiple of this one. And hopefully you can already see that if I were to put these things equal together, if I were to say that 5 to -4 is going to equal some scalar, or rather, let's start with BC, since that's the big one. 10, -4, -8 is going to equal some scalar value, some k, times my vector AB, 5, -2, -4. And maybe you're already seeing here that if I just double all these values, I get this. So really I could say that k is equal to 2. So by using some scalar multiple of this vector AB, I get BC. Therefore, these things must be collinear. And then if I think about this again, if I want to compare the ratio between these two, since this is the smaller and this is the larger, this one BC is larger by 2 times the size of AB. So we could say then that vector BC is equal to twice the vector AB. So that must mean then, if I were to compare the ratio of BC to AB, this has a ratio of 2 to 1, since BC is twice the length of AB. So we did a whole bunch of stuff there. Really, the key was finding what these vectors were, and then finding the scalar multiple that gets me to the larger, or I guess you could do the smaller vector. And then describing how we can use that scalar to describe the ratio between these two lengths. So I've got another example that's just like that, where I've got these three collinear points, prove that they're collinear, and then find the ratio that divides, where A divides CB. So pause this problem, see if you can give this one a shot, and we'll see how you did. All right, so here's all my work. You can check this over. I found that scalar multiple and then found that the ratio between these two must be -7 to 2. And notice that that negative does show up because it also shows the direction of this vector. These two are in opposite directions. Not only is this larger by a ratio of 7 to 2, but it's in the other direction as well. So hopefully this made some sense. In the next video, we're going to talk about something completely new, parametric equations. So I'll see you in the next video.